For years, the semiconductor industry treated one specific piece of machinery as the ultimate proof that certain technology simply couldn't be replicated outside a tiny handful of companies. Deep ultraviolet immersion lithography, the precision equipment used to etch the microscopic circuit patterns onto advanced computer chips, was considered so complex, so dependent on decades of accumulated engineering knowledge, that only one company on Earth, the Dutch firm ASML, had ever managed to build it at a commercial, reliable scale. Export controls from the United States and its allies were built directly around that assumption. Cut China off from ASML's machines, and you cut China off from advanced chip making. Full stop. Entire national policies, billions of dollars in trade restrictions, and years of geopolitical strategy were constructed on the premise that this specific technological bottleneck was, for all practical purposes, unbreachable without ASML's direct cooperation. This year, that assumption broke. A Chinese state-backed company has begun mass production of its own homegrown immersion DUV lithography machines, crossing a milestone that many people inside the semiconductor industry genuinely believed was years, if not a decade, away for China to reach domestically. Before we get into the technical details, it's worth acknowledging directly why a story like this deserves a careful, honest treatment rather than either extreme reaction. It would be easy to swing toward dismissing this entirely. Just 5 machines? Who cares? Or toward treating it as proof the entire global semiconductor order has already flipped overnight. Neither of those reactions actually serves you as someone trying to understand what's really happening in this space. The genuinely useful version of this story sits in the specific, verifiable details, which is exactly where we're going to spend the rest of this video. Let's actually understand why this specific piece of equipment mattered so much to begin with, because the impossible framing here isn't hyperbole. It reflects a genuine, widely shared industry consensus that existed right up until this milestone was actually crossed. Modern advanced chips are built by shining light through a mask to project incredibly precise circuit patterns onto a silicon wafer, layer by microscopic layer. Immersion DUV lithography specifically uses a thin layer of water between the lens and the wafer to bend light at a sharper angle, allowing finer, smaller circuit patterns to be etched than would be possible with light traveling through air alone. That single engineering trick, immersion, was itself a major breakthrough when ASML pioneered it commercially in the mid-2000s, and it remains foundational to how a huge share of the world's chips get manufactured today, sitting one tier below the even more advanced extreme ultraviolet, or EUV, lithography machines used for the very newest, most cutting-edge chip designs. It's worth pausing on just how counterintuitive that water immersion trick actually is, because it illustrates the kind of deep, accumulated engineering knowledge this entire field depends on. Adding a liquid layer between a precision optical lens and a silicon wafer sounds, on its face, like it should introduce more imprecision and contamination risk, not less. Making it work reliably at a commercial manufacturing scale required solving an enormous number of adjacent problems simultaneously, keeping the water layer perfectly uniform and free of bubbles, preventing any contamination of the wafer surface, managing the physical forces involved as the wafer stage moves at high speed beneath the lens, and doing all of this while maintaining positioning accuracy measured in fractions of a nanometer. That's the kind of compounding engineering complexity that takes an organization years of iterative refinement to actually master, which is exactly why so few companies worldwide ever attempted to compete directly with ASML in this specific space, let alone succeeded. Building a machine like this from scratch is not remotely comparable to reverse engineering a piece of consumer electronics. It requires an entire, deeply specialized supply chain, precise optics ground to tolerances measured in nanometers, incredibly stable mechanical stages that can position a silicon wafer with sub-atomic scale precision, specialized light sources, and software controlling the entire system with a level of synchronization that leaves essentially zero room for error. ASML itself took decades and absorbed several smaller specialized companies along the way to reach the point where it could reliably manufacture these systems at commercial scale. That history is exactly why so many analysts assumed China building a working equivalent domestically, especially under active export restrictions, specifically designed to prevent exactly this outcome, was a problem that would take many more years to solve, if it could be solved at all in any commercially meaningful way. So let's get into what actually happened, and how significant it genuinely is, because an honest assessment here needs to hold 2 things at once. This is a real, meaningful engineering achievement, and it also comes with real, important caveats about scale and maturity that are worth understanding clearly rather than glossing over in either direction. The company behind this achievement began actual mass production of these homegrown immersion DUV systems this year, marking China's first genuine commercial manufacturing effort for one of the most advanced and most tightly export-controlled pieces of chip-making equipment in the world. This gives Chinese chipmakers their strongest domestic alternative yet to Western lithography systems, and represents a meaningful, concrete step in Beijing's broader campaign to reduce its reliance on foreign technology after years of escalating export restrictions from the United States and its allies. But here's where the honest caveats matter, and where a responsible breakdown of this story needs to slow down rather than just running with the headline. Initial production volume is genuinely modest. Roughly 5 of these systems are expected to ship during 2026, with output increasing to around 20 machines in 2027. Compare that to ASML's own current scale. The company has stated it plans for a capacity of around 130 deep ultraviolet immersion machines in 2026 alone, with plans to add another 30% on top of that in 2027. 5 machines against ASML's 130 isn't remotely close to parity. It's a genuine proof of concept crossing into early commercial reality, not a company suddenly capable of replacing ASML's role in the global supply chain. To put that gap in a more concrete, relatable frame, imagine 2 auto manufacturers, where one has spent decades perfecting an assembly line capable of producing 130 cars a year with consistent quality and reliability, and a second manufacturer has just successfully built and sold its first 5 cars off an entirely new production line. The second manufacturer proving they can build a working car at all is a genuine achievement worth taking seriously. It is not the same thing as that manufacturer being ready to compete head-to-head on volume, reliability track record, or accumulated real-world operating experience. That's roughly the gap we're talking about here, and it's worth holding on to that image as a check against overstating what's actually happened. Industry analysts covering this story have specifically flagged several real technical hurdles that remain even after this milestone. Tool performance, meaning how precisely and reliably each individual machine actually performs compared to an established ASML system, is one open question. Scaling production of the machine itself, meaning China's ability to manufacture these systems consistently and repeatably at a growing volume, was specifically called out by analysts as, in their words, the most underestimated part of this entire challenge. Building 1 or 5 working machines in a lab or early production environment is a very different problem than reliably manufacturing dozens or hundreds of them with consistent quality, which is exactly the kind of manufacturing maturity ASML spent decades refining. On top of that, the broader surrounding ecosystem, specialized component suppliers, calibration expertise, the accumulated operational knowledge that comes from running thousands of these machines in production fleets over many years, takes time to build regardless of how capable any single machine coming off the line actually is. And there's a straightforward economic reality working against rapid adoption too. These new domestic machines are competing, at least in the near term, against ASML's existing, already fully depreciated machines already installed and running inside Chinese fabs, which changes the economics of when and how quickly domestic tools actually get adopted at scale, even where they're technically available. It's worth being clear about what fully depreciated actually means in this context, and why it matters more than it might sound. A piece of capital equipment that a factory purchased years ago and has already paid off, from an accounting perspective, effectively costs the operator very little to keep running. The expensive part, the purchase price, is already sunk. A brand new domestic machine, even a genuinely capable one, has to justify its full cost against that comparison, not against some abstract, idealized alternative. That's exactly the kind of unglamorous practical economic friction that tends to get lost in headlines about a technological breakthrough. But it's a real factor shaping how quickly this milestone actually translates into meaningfully more Chinese-made chips coming off Chinese-made equipment. This same dynamic plays out constantly across every capital-intensive manufacturing industry, not just semiconductors. And understanding it as a general pattern helps explain why genuine technological capability and actual market adoption can move at such different speeds. A factory operator making a purely rational short-term financial decision will often keep running older, paid-off equipment for years after a technically superior alternative becomes available, simply because the math favors the sunk cost. Machine until it eventually breaks down or becomes genuinely obsolete for the task at hand. Only sustained policy pressure, a genuine performance gap too large to ignore, or the older equipment's natural end of life tends to overcome that inertia, which means the real-world adoption curve for these new domestic machines will likely trail their technical readiness by a meaningful margin, purely as a function of ordinary industrial economics, rather than any remaining technical shortcoming. This DUV lithography milestone doesn't exist in isolation either. It's landing as part of a much broader pattern of Chinese semiconductor self-sufficiency progress that's been building steadily over the past couple of years. And understanding that wider context helps explain why this specific milestone landed the way it did. As of the start of this year, China had already reached roughly 35% domestic semiconductor equipment self-sufficiency, meaning that share of the specialized manufacturing tools used inside Chinese chip fabs are now sourced from domestic Chinese suppliers, rather than imported from abroad. That's up from roughly 25% just 2 years prior, and it notably crossed the 30% threshold that Beijing itself had originally set as a target for the end of 2025. Driven by aggressive, sustained state-led investment and the pressing practical need to root around US-led export controls, Chinese manufacturers have been steadily moving beyond simply assembling chips designed and equipped elsewhere toward actually producing the complex, specialized machinery required to build those chips domestically from the ground up. Crossing a self-imposed government target ahead of schedule is itself worth sitting with for a moment, since it's a meaningfully different signal than simply hitting an arbitrary industry benchmark set by outside analysts. When a government sets its own internal target for a strategically important technology, and its domestic industry actually beats that target, it suggests the underlying investment and coordination effort is functioning at least as well as Beijing itself hoped, and arguably better, since exceeding your own target ahead of your own deadline is a stronger signal of institutional effectiveness than simply making steady, expected progress. It's genuinely worth naming the specific technical areas where the most striking progress has shown up over the past year, because self-sufficiency as a broad concept can otherwise sound vague and hard to actually evaluate. Real advancement has occurred specifically in fields previously dominated almost entirely by established American firms, specialized areas like ion implantation, a critical step in semiconductor manufacturing where dopant atoms are precisely embedded into silicon wafers to control the electrical properties of the finished chip, and the advanced lithography systems we've spent most of this video discussing. These aren't peripheral, easy technologies. They're specifically the bottleneck technologies that export controls. Policy was designed around on the theory that controlling access to this narrow, specialized set of tools would meaningfully slow China's semiconductor ambitions, regardless of how much raw investment or engineering talent Beijing threw at the broader problem. One specific, concrete example worth mentioning. In early January of this year, a Chinese state nuclear research institute announced successful validation of a specialized ion implantation tool, representing the country's first domestically developed system of its specific kind. That's a genuinely narrow technical achievement on its own. Most people outside the semiconductor industry will never need to know or care what ion implantation is, but it's exactly this kind of accumulated, narrow, technically unglamorous progress, tool by tool, bottleneck by bottleneck, that adds up over time into the broader 35% self-sufficiency figure, and eventually into milestones as visible and significant as the DUV lithography breakthrough we opened this video with. There's a genuine, almost paradoxical irony sitting underneath all of this that's worth naming directly, because it connects to a pattern this channel has actually covered before in different contexts. Sustained pressure and restriction, rather than permanently blocking a country's technological progress, can instead accelerate a determined, well-resourced effort to build an independent alternative from scratch. Some analysts covering this trend have specifically described it as acting like a catalyst rather than a deterrent. The restrictions didn't stop China's semiconductor ambitions. They redirected an enormous amount of state investment and engineering talent specifically toward building a parallel, self-contained supply chain that doesn't depend on the restricted technology at all. Whether that outcome represents export controls fundamentally failing at their stated goal, or simply working more slowly than originally hoped, while still imposing real, meaningful costs and delays along the way, is a genuinely contested question among policy analysts, and reasonable people looking at the same set of facts land in different places on it. Alongside this hardware story, there's a parallel related development worth understanding, because it shows this isn't purely an equipment manufacturing story in isolation. It's connected to China's broader chip design ambitions too. This past May, Huawei announced its own chip design breakthrough, specifically targeting a path to producing cutting-edge chips within the next several years. The company stated that by 2031, its high-end chips would achieve transistor density equivalent to what's known as a 1.4 nanometer manufacturing process, a measure of how small and densely packed the individual circuit elements on a chip actually are, with smaller numbers generally meaning more computing power and efficiency packed into the same physical space. It's worth being precise about what Huawei is actually claiming here, because there's an important technical distinction between chip design and chip manufacturing that's easy to blur together. Huawei's announcement is specifically about achieving equivalent transistor density through advanced chip design techniques, not necessarily through manufacturing the chip at a literal 1.4 nanometer physical process node the way TSMC does. This is a meaningfully different technical path, essentially achieving similar performance and density characteristics through clever architectural and design choices, potentially without requiring the same bleeding-edge manufacturing equipment that a literal 1.4 nanometer process would otherwise demand. That distinction matters because it suggests Huawei may be pursuing a genuinely different strategy for closing the gap, rather than simply racing to build an equivalent to TSMC's most advanced fabrication process directly. To put that number in real, honest context, China's most advanced current chip-making capability is generally believed to sit around 7 nanometers today, considerably behind Taiwan-based TSMC, the world's leading advanced chip manufacturer, which currently uses 2 nanometer manufacturing technology and has stated plans to begin mass production using an even more advanced 1.4 nanometer process by 2028. So Huawei's own stated roadmap, even if it lands exactly on schedule, would put China's most advanced domestic chip capability at a point in 2031 that TSMC expects to reach 3 years earlier, in 2028. That's a real, still substantial gap. Genuine progress toward closing a technology lead, not evidence that the gap has already closed. It's also worth being appropriately skeptical of any company's own multi-year roadmap announcement, regardless of which country that company is based in. Corporate roadmaps, stretching 5 or more years into the future, are inherently uncertain, subject to unforeseen technical obstacles, shifting resource priorities, and the simple reality that ambitious engineering timelines slip more often than they arrive early. Huawei, stating a 2031 target for itself, is a meaningful signal of the company's own confidence and strategic direction, but it's not the same thing as a guaranteed, already achieved outcome. Treating any company's forward-looking roadmap as settled fact rather than a stated intention subject to real execution risk would be an analytical mistake regardless of which side of this technology competition you're rooting for. There's a specific comment from a senior Huawei executive worth including here because it captures the broader dynamic driving all of this in a genuinely striking, direct way. Huawei's rotating chairman and deputy chairman suggested in a recent interview that the company is, in his own words, thankful to the US government for helping spur this chip technology growth, adding that if the US hadn't forced the issue, the country, the companies, and the industry as a whole wouldn't have pursued this path with nearly the same urgency. That's a remarkably candid acknowledgement of the exact dynamic we just walked through with the DUV lithography story. Restriction and pressure functioning as an accelerant for independent development, openly stated by one of the companies most directly affected by the restrictions in question. It's genuinely rare and worth sitting with for an executive at a company directly targeted by a specific government's trade policy to publicly frame that policy as having ultimately benefited their own company's long-term strategic position. That kind of statement isn't the sort of thing typically said for purely diplomatic reasons. Companies facing genuinely crippling restrictions usually emphasize the damage and disruption caused, not gratitude for having been forced into a harder path. The fact that this specific framing came from Huawei itself, a company that has spent years navigating direct sanctions, adds real weight to the broader restrictions as accelerant thesis running through this entire story, rather than that thesis being purely an outside analyst's interpretation imposed onto the facts from a distance. It's worth situating all of this inside China's own official framing of the past year, too, since that framing tells you something about how seriously Beijing itself is treating this progress. China's own president described the past year as a year of breakthroughs, specifically for the country's artificial intelligence and semiconductor chip companies, stating that these technologies had, in his words, reached new heights. When a country's top leadership specifically singles out semiconductor progress in a major annual address, that's a meaningful signal about how central this specific technology race is considered to the country's broader strategic priorities. Not simply an industry-specific story confined to trade publications and specialist analysts, but a piece of the national strategic conversation happening at the very highest level of government. It's worth noting, too, how these annual address comments function as a kind of institutional scorecard, distinct from the more granular, technical claims coming out of individual companies like Huawei. A national leader publicly framing an entire technology sector's progress as a headline achievement for the year signals that continued investment, continued state support, and continued policy priority in this space should be expected going forward, rather than this being a one-off push that might quietly wind down once the immediate pressure from export controls eases. That's a meaningful signal for anyone trying to forecast whether the trajectory we've described here is likely to continue at a similar pace, or whether it might slow down once the most urgent, externally imposed pressure driving it starts to ease. So let's step back and actually answer the question. This video's title is really asking, did China genuinely do something that was widely considered impossible? The honest answer, held with appropriate nuance rather, than flattened into a simple yes or no, is that China crossed a milestone that was genuinely widely considered to be many years away under the current export control regime. And that milestone is real, verifiable, and technically significant, but crossed a milestone many considered years away is meaningfully different from solved the entire underlying problem and achieved parity with the global leader. 5 machines in 2026, scaling to 20 in 2027 against ASML's roughly 130 plus annual production capacity, is a genuine breakthrough in capability, not yet a genuine shift in competitive balance. Both of those things are true simultaneously, and treating this story as either a total non-event or a complete overnight reversal of the global semiconductor order would both be dishonest readings of the same underlying facts. This is really the core tension running through every story in this space, and it's worth naming as a general pattern rather than something unique to lithography machines specifically. Genuinely impressive engineering milestones and genuinely large remaining gaps can, and very often do, coexist in the same story. A headline demands you pick one framing or the other. Either China caught up, or China is still way behind. But the actual honest technical reality sits in the uncomfortable middle ground between those two framings. And staying in that uncomfortable middle is usually where the more accurate picture actually lives. What makes this genuinely worth your attention, rather than just another data point, in a long-running geopolitical rivalry story, is what it suggests about the actual effectiveness and long-term trajectory of technology export controls as a policy tool more broadly. The stated theoretical goal of these restrictions was to meaningfully slow China's ability to develop cutting-edge semiconductor manufacturing independently. What's actually happened, based on the evidence we've walked through here, is a genuine slowdown relative to where China would plausibly be without any restrictions at all, combined with a determined, well-funded, state-backed effort that's now producing real, if still modest-scale, independent alternatives faster than many analysts originally expected. Whether you view that as the restrictions ultimately failing, succeeding at a more limited goal than originally advertised, or simply buying time whose value depends entirely on what happens with the technology gap over the next 5 to 10 years, is a genuinely open, actively debated question, rather than one with a single settled answer. It's worth thinking through what the next few years plausibly look like from here, purely as an exercise in reasoned extrapolation rather than confident prediction. If the current trajectory holds, modest but real annual increases in domestic lithography production volume, continued progress on the broader self-sufficiency percentage, Huawei's chip, design roadmap proceeding roughly on schedule. The gap between China's domestic semiconductor capability and the global leading edge should continue narrowing gradually rather than closing suddenly. That's a meaningfully different story than either extreme. It's neither a permanent, unbridgeable gap that export controls successfully lock in place forever, nor a rapid catch-up that erases the current lead within a couple of years. Gradual, sustained narrowing, playing out over the better part of a decade, driven by accumulating small technical wins rather than any single dramatic breakthrough, is the pattern the evidence we've walked through actually supports. I want to know how you're reading this story. Does a milestone like this, real progress, but still a substantial way from actual parity, change how you think about the broader US-China technology competition? Or does it mostly confirm what you already expected to happen eventually? Do you read this as evidence that export controls are ultimately failing at their stated goal, or as evidence that they're working roughly as designed, just more slowly and at a higher cost to Beijing than a total permanent block would have been? Tell me in the comments, because I think this is exactly the kind of story where reasonable, well-informed people can look at the identical set of facts and land in genuinely different places. And I'd like to hear where you land and why. If you want more grounded, honest coverage of where technology, geopolitics, and manufacturing actually intersect, without inflating a genuine milestone into an overnight revolution, or dismissing real progress just because the gap hasn't fully closed yet, subscribe, hit the bell so you don't miss the next one, and I'll see you in the next video where we'll keep tracking exactly how this gap actually narrows over the years ahead, rather than declaring it closed or unbridgeable before the evidence actually supports either conclusion.